Now that we've taken some time to learn a little bit more about the covalent compounds and how to draw them and how that structure affects their outer behavior, I think it might be a good idea before we completely leave this section to take a couple moments and review nomenclature, or how we name things. Now, in order to do that, we're going to start all the way back in the very beginning. Now remember that there are three basic types of bonds between atoms. We have our nonpolar covalent, polar covalent, and ionic bonds. And in order to identify the difference between those types, you need to subtract the electronegativity numbers. If the difference in electronegativity is somewhere between 0 to 0.3, you may even see this all the way up to about 0.5, depending on your source, the bond is considered to be nonpolar covalent. Polar covalent is somewhere in the range of about 0.3 to about 1.7, and ionic, of course, would be above 1.7 all the way up to about that 4.0 mark. So I have two examples here on the screen. I just want to take a second to quickly review what type of bonding exists between these atoms. So we would look up the electronegativity numbers, first for sodium and then for chlorine. Sodium 0.9, chlorine 3.2. Subtract them and you find the difference is 2.3. That would give NaCl an ionic bond. Whereas CH4, again, it doesn't matter that there's more than one hydrogen there. There are four of them. We still only subtract one of each of those numbers, one for carbon and one for hydrogen. So carbon is 2.5, hydrogen is 2.1. Subtract them and the difference is 0.4. And that would give us a polar covalent bond. Now that we have kind of gained the ability to tell the difference between these different types of bonds, it's important to see how that's going to affect how we name the compounds that result. So the most important thing to note here is that nonpolar covalent and polar covalent both have that word covalent. The electrons are still being shared. And because of that, we're going to kind of blanket statement say that we're going to name compounds with any style of covalent bonding. They're always going to have the same style of naming. So let's take a couple moments to look into this covalent nomenclature. I'm going to start you right out of the gate with an example, CCl4. So we have a couple of problems here. Unlike in ionic nomenclature, we don't have any ions, we don't have any charges, there's no crisscrossing. So what are we going to do to have kind of an important distinguishing characteristic to put inside the names? In ionic, the name reflected everything about that ion, and yet there's no ions here. So, what do we do for naming? Well, you might notice that the only real big distinguishing feature of this particular compound is not only the two elements that are in it, but also the subscripts that come along with that information. And just one more time, the subscript tells you how many of that atom is present on the inside of that compound. That's going to be pretty important. So we're going to represent these subscripts by using prefixes. And again, this is only for covalent compounds. Once students typically learn about prefixes, they want to put prefixes on everything, and that will not work. That's not normal. So please only use prefixes with covalently bonded compounds. Always double check that difference in electronegativity. Now by prefixes, this is what I mean. They're words that will represent the number of that particular atom that's in the compound. So we'll substitute mono for 1, di for 2, tri for 3, tetra for 4, penta, hexa, hepta, octa, nona, and deca, all the way out through 10. So what is this particular compound trying to convey to us with its condensed, beautiful little formula of CCl4? Well, it's trying to tell us that it has 1 carbon and 4 chlorines. So now let's spiff that up with a little bit more chemistry ease. I'm going to take some time here to kind of change out the numbers for the prefixes. So instead of 1, I'm going to say mono, and instead of 4, I'm going to say tetra. Now there's a couple other little things that I need to fix about this naming system. First thing you do need to know is we absolutely never start a compound, when naming a compound, by saying the word mono. So I'm just going to eliminate that from the get-go. It's a bit redundant. We already know that there's 1 carbon in here. We don't have to say 1 carbon. By simply saying carbon, we're admitting that there's at least 1 in there. And then the second thing, the second element always is going to end in the three-letter sequence "ide." So I'm going to take off the ending and replace it with "ide." And now just smush together what's left over. Carbon tetrachloride. Now, just so that you can kind of make a little bit more sense of this, I've tried to write down some steps to make this a little bit easier for you. So the first thing you're going to want to do again is just to name both elements. In this case, it would have been carbon and chlorine. Add prefixes for each element to represent the subscripts. There was only one carbon, so we said mono. Then there was 4 chlorines, so we said tetra. Change the ending of the second element to ide, I-D-E. So instead of chlorine, it became chloride. And then, of course, eliminate mono from the very, very front part. You can use it in between the two elements, but you can't use it out in front. And that, again, is because it's kind of redundant to say so. So how about a couple more examples so that you can kind of really get this cemented in your brain? How about this example? P2S5, definitely a covalent style bond. So if we take a look, this is trying to tell us that we have 2 phosphorus and 5 sulfur. So I'm going to start to replace some of the information in here. Instead of 2, I want to say di. Instead of 5, I want to say penta. Instead of sulfur, I want to say sulfide. Squish together what remains, and here's your name, diphosphorous pentasulfide. That was a nice easy one. Let's try another one. How about H2O? Yes, I know that you know that that's water. That's its common name. But according to the covalent nomenclature scheme, we could actually call it something different. So this is trying to communicate to us that we have 2 hydrogens and 1 oxygen. Again, you're going to replace the prefixes. So instead of 2, we're going to say di. Instead of 1, we're going to say mono. And instead of oxygen, we're going to say oxide. Now, I want you to pay very careful attention here when I smush this all together. You are allowed to keep the mono in between the two. That doesn't have to be eliminated, but something else does. Check it out. That's right. When the mono and the oxygen smushed together, we would have had 2 O's repeated, one right after the other. And that's a lot of O's to write down. So we just eliminate one to make it flow a little bit better. Dihydrogen monoxide. How about this example, SF6? Well, this is trying to communicate to us 1 sulfur and 6 fluorine. Again, replace the numbers with the correct prefix. Instead of 1, I would put mono. Instead of 6, I would put hexa. Instead of fluorine, I would put fluoride. Eliminate anything? That's right, the mono gets taken away from out in front. And then push together what you have left. Sulfur hexafluoride. Wonderful job. Now, before we completely leave this topic of covalent nomenclature, I want to make sure that we practice with the reverse direction. What happens when you're given a name and you're asked to provide a chemical formula? Well, we just need to decode this, but in the opposite direction. So what is diphosphorous pentasulfide trying to communicate to us? Well, the prefix di means 2, and the prefix penta means 5. So write it down. It's saying 2 phosphorus and 5 sulfurs. Now, instead of the phosphorus full name and sulfur full name, write out the element symbols, and instead of the numbers in front, write them as subscripts. P2, S5. Now, I think a little practice might be in order. So I did get you some practice problems here. What I'm going to suggest is that you get a pencil and a paper and try to translate these. If you're given a name, provide a formula. If you're given a formula, provide a name. Scribble them down on that piece of paper and push pause on this video. When you have all of those answers, then unpause the video to reveal those answers. All right, so now that you've had a chance to take a look at these lovely problems, it's time to reveal the answers. All right, so chlorine dioxide would be translated to ClO2. Dinitrogen trioxide would be N2O3. Tetraphosphorous pentasulfide would be P4S5. Disilicon hexabromide is the name of Si2BR6. Nitrogen trifluoride would be NF3, and hexaboron monosilicide, yeah, that's a mouthful, it would be the B6Si. Again, if you have any questions, please feel free to contact me for some help. Otherwise, good luck with your covalent nomenclature.